Hey y'all. So far in our class, we've been dealing a lot with polynomials, particularly factoring quadratics, identifying the key features of polynomials, such as the y-intercept, the x-intercept, and behavior, and sketching the graphs of them. Now, so far, I hope that you found that it's not too difficult to figure out these features of the polynomials, such as the y-intercept. You just plug 0 in for x to find the y-intercept. For the end behavior, it's all about looking at the leading term, right? And then for the x-intercepts, it's all about setting the equation equal to 0 and solving. Usually we would solve that through factoring. Now, so far, if I ever asked you guys to factor, to solve, it was always with a quadratic. But today, what I want to do is look at some more advanced polynomial factoring techniques so that we can solve for the intercepts of any polynomials and be able to start understanding the functions of polynomials of higher degrees that are greater than 2. All right. So before we get started, I just wanted to give a little shout out to Mark in our Discord server. Mark has been creating some very, very beautiful emotes, as you can see. This one in particular is extremely gorgeous for our server. If you would like to submit ideas for emotes for our Discord server, I fully encourage you. You can do that over in the Discord emote suggestions text channel on our server. All right, now let's get into some advanced polynomial factoring techniques with something that's a bit of a classic, difference of squares. So difference of squares is an idea that if I have a binomial, this is called a binomial because there are two terms, right? Two terms. If I have a binomial and the two terms of my binomial are subtracting each other, then I should be able to factor it such that my factors are the roots of the two terms, just subtracted, then added, multiplying each other. So what does this actually look like? So difference of squares is kind of like the oldest trick in the book. It's like super common to see a problem have difference of squares. For example, suppose I have a binomial such as x squared minus 4. If I was asked to factor this binomial, I can identify that x squared is, well, x being squared, and 4 is, so x squared is x to the power of 2, and 4 is 2 to the power of 2. So this is a difference of squares. We call them squares because they are to the power of 2, right? So according to my idea of this formula, I should be able to say that this is factored into their square roots subtracted. So x minus 2 times their square roots added, x plus 2. Now, why is it that I'm allowed to do this? Well, to see that it would be useful for us to try out foiling, multiplying out these binomials that are multiplying each other to just sort of see what we get as a result. So let's do with the top first. A times A would be A squared. So far, so good. A times B would be AB. Negative B times A would be minus AB. And minus B times B would be minus B squared. Yeah? That's a lot of B's, huh? All right. So then, now that I've foiled it, I should probably simplify my middle terms. What would be plus AB minus AB? You guessed it. They cancel out. So as a result, I am left with A squared minus B squared. So see how even when I use variables, right, when I'm in its most general form, this is true. Try out down here. X minus 2 times x plus 2. If I multiply it out, I get x squared plus 2x minus 2x minus 4. So 2x and minus 2x cancel out, and I'm left with x squared minus 4. Identifying when difference of squares is occurring is super important. It's going to be so common that that if you have two terms subtracting each other and you're trying to factor, it's going to be super common that it's a difference of squares problem. So just make sure that you guys are on the lookout for such problems. Now, here I have 4 different examples of binomials with subtraction between the terms. What I'd like y'all to do is take a moment, pause the video please, and think about which of these binomials can you factor using difference of squares? And then go ahead and try to factor them yourself. Now, hopefully you've paused the video and thought about this, but let's get going. So this was actually a bit of a trick question here. I can actually factor all 4 of these with difference of squares. So x squared minus 9, that one's pretty obvious. These are both squared values, so it would result in x minus 3 times x plus 3, because the square root of x squared is x, the square root of 9 is 3. Cool. The second one, hey, you don't always have to have numbers for your difference of squares to work. So if I have 2 variables that are squared and subtracting each other, I can still factor that into x minus y times x plus y. Cool. The third one is an example where you don't always have to have your variable in front, like how these ones have shown. I could actually have the variable be the one subtracting. I would just need to keep that in mind, and the way that this would factor would be the square root of 4 is 2, so I'd have 2 minus x times 2 plus x. Notice how, because the terms were flipped, the terms are flipped inside the factors. Finally, number 4 here, this is kind of the tricky one. A lot of people don't think about it, but I don't actually need to have perfect squares to do difference of squares, right? The square root of a squared is a. What's the square root of 3? Well, it's square root 3. So this guy could actually technically be factored into a minus square root 3 times a plus square root 3. So that's another little trick there. I can actually always use difference of squares if I ever just have a binomial and they are subtracting each other. It just happens to be that some cases, like the first 3, tend to be more common and more useful to factor than this 4th one. But it is an opportunity. The next special case for us to take a look at is very similar to the last one, but this one's difference of cubes. So it's just like difference of squares, except instead of my binomial terms being to a power of 2, they are to a power of 3. So this one's a little bit less common. However, it does still exist. And when you have a difference of cubes, it should factor into this form. So if I have a cubed minus b cubed, then it would factor into a minus b times a squared plus ab plus b squared. Now, just to verify that for ourselves, let's go ahead and multiply these factors together just to confirm that it is actually indeed correct. So a times a squared would equal a to the power of 3. So far, so good. A times ab would be a squared b, and a times b squared is a b squared, right? Okay, now let's look at minus b. Minus b times a squared would be minus a squared b. Minus b times ab would be minus ab squared. And minus b times b squared would be equal to minus b cubed. Now what we need to do is we need to cancel out the terms in common. So a squared b minus a squared b, those will cancel out. ab squared minus ab squared will cancel. And what am I left with? I'm left with a cubed minus b cubed. So now that we are confirmed and convinced that this factoring works, right? Because I did it in general terms, right? This is why we use the variables, y'all, so that I can know that no matter what a and b are equal to, this will always be the case. So let's try an example then. What if I have x to the power of 3 minus 27? Now, this is where difference of cubes can be a little bit trickier because we're a lot more familiar with the perfect square numbers. We're a lot more familiar with numbers that are like, 4 is 2 squared, 9 is 3 squared, 16 is 4 squared. The powers of 3 we're not as familiar with typically. But if you do see a term that is to a power of 3, being subtracted by another number, it's a pretty good idea to at least think about difference of cubes. So let's think about what would these guys be. Well, I know that x cubed is x to the power 3. 27, I actually know that that is 3 to the power 3, right? Think about it for yourself, right? 3 to the power 3 would be 3 times 3 times 3. 3 times 3, 3 times 3 is 9. 9 times 3 is 27. Cool. So then what would this factor into? Well, it would be a minus b, so x minus 3. Times a squared, so x squared, plus ab, so x times 3, so that's plus x times 3 is 3x, and then b squared. Well, my b value we said was 3. 3 squared is 9, so plus 9. Let's make sure that that actually is true, though. So I'm going to multiply it back out. So x times x squared is x cubed. X times 3x is 3x squared. X times 9 is 9x. Minus 3 times x squared is minus 3x squared. Minus 3 times 3x is minus 9x. And minus 3 times 9 is minus 27. What do you know? Look at it. Look at this. 3x squared, negative 3x squared cancels. 9x minus 9x cancels. And what am I left with? I'm left with x cubed minus 27. So this is my factored form for my difference of cubes. The last special case factoring little trick that I want to look at is sum of cubes. So the last two special cases were always difference of squares, difference of cubes. It was when they were subtracting. This one, actually, when you have two terms that are to a third power and they're adding, there is also a special case. So if I have a cubed plus b cubed, then that should factor into a plus b times a squared minus ab plus b squared. Once again, let's verify that that's true. So a times a squared is a to the power of 3. A times minus ab is minus a squared b. A times b squared is plus ab squared. B times a squared is a squared b. B times minus ab is going to be minus ab squared. And b times b squared is going to be b cubed. So what cancels out here? Minus a squared b and plus a squared b. ab squared and minus ab squared. And I'm left with a cubed plus b cubed. Something that I want to... So it works, right? So something that I want to point out here before we go and do an example. Sum of cubes is the only time that it's factorable with the addition. There is no sum of squares, okay? So if I have a squared plus b squared, that will not factor. That will not factor, okay? Once again, I just want to point this out. A squared plus b squared does not factor. All right? It is exclusive. The sum is only for cubes, okay? So let's look at an example. What if I had, let's see, what if I had 64 plus y to the power of 3? So we know y is obviously y to the power of 3. What's 64? 64 is actually 4 to the power of 3 because 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 64. So what does this factor into? Well, the cube root of 64 is 4, as we just saw. So I would have 4 plus y times 4 squared, which is 16, minus ab, so that'd be 4 times y, so minus 4y, plus b squared, that'd be y squared. Cool. I think that I'll leave multiplying this out as an exercise for the viewer. That's the end of my first part about advanced factoring techniques for polynomials. There's going to be another part to this video series, and that one will be about the rational zeros theorem. That's a much more general topic, and I think that I want to dedicate a single video to it.